All right. So welcome everyone to another SNAPP seminar. It's great to see you all. As always, please mute your audio and if possible, keep your videos on. That makes it very lively. The slides are available on the SNAPP website and I will copy the link to the chat box soon. Please feel free to type your questions in the chat box. There'll be a few short pauses during the talk when you can unmute yourself and ask the questions to the speaker. And there will be, of course, a longer Q&A session at the end of the talk. So today we are excited to have Professor Jim Dai here to speak in today's seminar. Jim is a presidential chair professor at the Chinese University of Hong Kong, CUHK, Shenzhen, and the Leon C. Welch Professor of Engineering in Cornell University. From 1990 to 2012, he was on the faculty of Georgia Institute of Technology. Jim received his BA and MA in mathematics from Nanjing University and his PhD in mathematics from Stanford University. His research area is in applied probability, focusing on stochastic processing networks and recently on reinforcement learning. Jim has received several awards and accolades, including the Erlang Prize in 1998 and the ACM SIGMETRICS Achievement Award in 2018. He served as the editor-in-chief for Mathematics of Operations Research from 2012 to 2019. Jim, welcome, and the floor is yours.
Thank you. Thank you. It's great to see many old friends after so many years. It's great to see you, albeit online, not in person. I also want to thank this committee. This has done a fabulous job getting these talks, seminar talks, going despite the pandemic. So particularly Siva, the banker, Christina, and Wayna. So thank you for the invitation. So this talk is many keywords here: Stein method, diffusion approximation, high order. Today's the keyword here, you should focus on high order. And you may have heard this before, over the years, you heard my talk, right? Maybe this term used. And today there's something that, frankly, that I was struggling for several years on this problem. And I think finally we have a much better understanding. So I hope today I will share, basically bring you up to date, the latest on this front. There are many open problems, okay, because of this the latest development. So you will see that at the end of this talk. I hope you can hear me okay, everything, right? In technology-wise.
Yes.
Okay, great. Let's see, that's how do I move? The next page. It's a bit, okay, so this joint work, first of all, with Anton, Braverman, and Xiao, Fang. Xiao is a professor at the CUHK in statistics department. His thesis, he did his PhD at the NUS, working with Louis Chen. Some of you know that in Stein community, Louis Chen is a big figure. So we are very grateful that, I'm very grateful that he's a collaborator on this work, pushed it very, very far with his joining the team. I also want to thank this group. Yi Hong is a PhD student currently at CMU. And Zhu Yang Liu, she's currently PhD at Stanford GSB, and Pan Yi is at Purdue University, and Zhu Zong, they all helped in various ways on this project in multiple years. So today's outline, I'm going to talk about, spend a fair amount of time on background. Then on the one-dimensional, focus on one-dimensional diffusions, okay, this one here. although toward the end, I will talk about multidimensional as well. And then I really focus on three models, okay? 3 Markov chain models, okay? And to illustrate this methodology. And I will state concluding remarks at the end. So this is to help you, to give you general direction, my talk is going, that let me just state this central limit theorem. So you have, this is classical IRD setting. This is a partial sum here. I still get used to this thing here. Okay, so Wn is a partial sum properly normalized, right? Converge to a normal standard, normal random variable. All right. So that's limit theorem. Now we also know there's a very SM bonds, and this bonds can kept being improved. And the last time was as 2012. This is the so-called, this is the, as far as I know, this is the best bond here. And the left side here, this side is a so-called distance, is a co-Markov distance. Co-Markov distance between this Wn, let's call it this prelimit, and Z is a limit. Okay, so prelimit and limit, the difference, these two distributions. Okay, so this Berry SM, but these best proofs are actually not using Stein method. So I just want to mention Stein method can produce this kind of bonds. Okay, it's aiming at can produce this kind of bonds, and but typically it's not provide base constants. Okay, may not be able to provide base constant. So a few comments about this this bond here is that this is not a limit theorem, right? There's no limit, and there's no need n go to infinite. So n is fixed, right? Okay, so although sometimes I call this this a prelimit, Wn, Z is a limit, but it's really, it's not, there's no limit here, right? So Wn is one model, Z is another model. You just compare the difference of two models, okay? So that's this result here. So this is saying same thing here, okay? So the main thing here is the last bullet point, okay? Is there any alternative Z to adopt, okay? Not necessarily normal random variable, right? But for, with a similar computational complexity as normal, okay? But better error bound, okay? So that's the general research direction. So indeed, I'll make it more precise in the next in the next slide. But you know, just point out in the literature, people already go beyond normal, right? The Stein did normal. Louis Chen, he's started with PhD thesis at Stanford, did a Poisson approximation. Poisson is the limit random variable and other random variables. Okay, so that has been done in literature. And in our context, okay, and many of you here, the audience, is interested in the stochastic networks in our context. So this W, what we have is a stationary diffusion of Markov chain, okay? And this Markov chain indexed by some parameter of natural parameter of interest. And generally, this Markov chain is complex. Although today, in this talk, you may not be able to see that general. So this may be related to general Markov chain for stochastic networks. Has a lot of complexities there. So with approximation Z, okay, our approximation Z is equal to, I'm using Y here, is a stationary diffusion for some diffusion process. So we're going to use the stationary diffusion for some diffusion process to approximate this prelimit Wn. Now, again, this is not a limit theorem, okay? It's not a limit theorem. It's going to be have two models to compare, okay? So, and Y should be attractive in some way. And to me, at this point, easier thing to think about computationally. It's easier to compute, okay? But it may have other benefit, okay? And I think there's no need for me to motivate this because experts are here on the among the audience. Okay, so here the number 4 here is right, the general idea. If the generator of the Markov chain is close to the generator of the diffusion process, in some sense, okay, in some sense, Then this is a two-station distribution. W is a station distribution for Markov chain. Y is a station distribution for the diffusion process should be closed. And this claim is often now can be justified by Stein's method, okay? And the topic, okay, the focus of this talk is there are many candidate diffusion process, which diffusion to choose, right? That's really the main topic of today's talk. All right, so maybe before I go on, is there any burning question here? Something that let me pause for 30 seconds. That's a direction. So I hope I didn't get you lost from beginning.
There is no question in the chat box.
Chat box, okay.
There is no question in the chat box.
All right, good. All right, so well, I apologize that something the many name, I mean, the experts here are the name, the literature is not listed here, but today's talk is very narrow, right? Very narrow, so that I want to apologize in advance that many of your work is not cited here. Okay, so let me just give a background. Start with a Markov chain. Okay, discrete time is indeed a simplest discrete time Markov chain model. All right. So everybody can understand, okay? So even the first year graduate student, right? So X is Markov discrete time Markov chain. Suppose I use this example, state space S has 3 states, 1, 2, 3, and a transition matrix. So we know this one, you can compute station distribution pi, right? So station distribution, okay, station distribution satisfy balance equation, all right? Or equivalent say pi equal to G, and I introduce this, allow me to introduce notation G called a so-called generator for discrete time Markov chain. Usually you're dealing with the discrete time Markov chain, the term generator never show up, all right? But I sort of artificially impose or introduce this term here, the generator here. So simply it's a P minus I, and P is the transition matrix. What you can see that this equation 1, okay, equation 1 is pi G equal to 0 is really equivalent to this one here. The next one, the red one here, pi G times every column vector F equal to 0. If every column vector equal to 0 here, equivalent to pi G equal to 0. But if you look at the here, let me close this. If you look at here, this one here, it's simply this says that this expression here simply equal to expect value GF. GF evaluate for this random variable W is following the station distribution. Okay, so that's just this definition here. So for some of you may be familiar with, for some of you first time see this notation. So W is a random variable that having the station distribution is characterized by this GF applied G is generator applied to function F, any function F, and this evaluated this for this random variable is value equal to 0. And if this is true for all F, all good F, then that W is nothing but having station distribution. So this equation here characterizes station distribution. All right. So that's all I want to say on this slide. So the next slide is talking about diffusion. Okay. So I intentionally not to get into multidimensional diffusion at this point. I want to focus my talk very focused, okay? So that everybody understands. Let's consider one-dimensional diffusion. So you're given 2 functions. B is a drift function, okay? B is a drift. And V is this related to variance or variance function here, but V, okay? And so this is a stochastic differential equation, right? Solving here, B is the Brownian motion, you solve a solution, and Y is such object Y exists, YT, that's called diffusion process. And since I explicitly need to refer to the drift and this variance function, so I call BU diffusion, okay, so it's diffusion, all right. This BU diffusion has a generator, okay, and generator the B times the first order derivative and V times the second order derivative. Okay, So that's the generally defined generator. I don't want to get into that. Indeed, there's a defining property for something to be generator. Okay, for sake of time, I'm not going to get into that. So the point is this diffusion process Y, if it has state distribution, this diffusion process has state distribution. So the Y has a stationary distribution, okay, stationary density pi Y, if only if this stationary density satisfies this equation. And if this one, if you remember what I did last on the previous slides for the Poisson, right? This is simply if space G f of Y. Okay, Y has a stationary distribution. Okay, so GF. So this is the same as the in at least in the in format, the same as the Markov chain case. Okay, so this equation is the characterized distribution, and this is actually in the reflex boundary motion context. Lewis Williams and Mark Harrison called this base agile relationship, and it's featured in Tom Kurtz, ECA Kurtz. There's results on this with a various version of this result in ECA and Kurtz. Okay. So in this one-dimensional case, this equation characterization here, base agile relationship, has an explicit solution. So solution given density is given by this formula here. All right. So it's a very. So let me go to the next slide to. How do I do this? Erase this. All right, so I'm going to, yes, basically repeat on the previous slides. So let's start over again. Pi is the stationary density for a diffusion process Y, if only if pi applied to the generator, this integration equal to 0, okay? And the generator, again, remind you here, the generator is this form, okay? And to connect with the first slides on Markov chain, the previous slides, this integral simply equal to space value GF evaluate this random variable Y having the stationary density pi, right? And I'm copying down space out GF exactly this last line here. So that's equal to 0, okay? So this already may have confused some of you. So that's, I'm going to next slides. Basically, I want to summarize what I said in the last few slides, okay? So if you completely confused already, this slides, okay? So wake up here. So this slide should be enough for you to carry over to the rest of this talk. I do need you to be familiar with these slides of the content, okay? So the first bullet point is a unique distribution Y that satisfies that, this one. Now I said I just ignored any technical assumptions, okay? Technical assumption on V, etc. B, okay? So basically at high level, so Y it says only one random variable satisfies this equation here, okay? This equation here, and that's for all F test function, okay? So there's only one Y. So given B, given V, okay? So there's only one Y. This random variable is characterized by this relationship here, okay? And the distribution of Y, indeed, this unique distribution has explicit form. Density is given by the next line here, okay? It's explicit here. Now, it's clear that actually, once you get to the multidimensional case, you don't have explicit form, okay? You can have a similar characterization like this equation, but you don't have explicit form, okay? You may have to compute from this equation here, you numerically the distribution Y, all right? The third thing is the distribution, this distribution, unique distribution is a distribution of the BU diffusion. Now, this really is background information, right? I really don't need, the rest of the talk don't need to use this third bullet point, okay? So I don't need to justify does this diffusion exist or something, so don't worry. But it's good to know the connection, right? So you know when you see this Y, what's this Y? What's this density? Oh, that's the state distribution for this diffusion process, right? It's a good way for help us to get organized, okay? So that knowing what we are, where are we going, okay? So let me give you one example is the standard normal random variable. How do I can clear this quickly? Okay, this one. Okay, yes. So this, suppose I want this distribution is a normal, okay? Standard normal random variable. It's a normal distribution like this. You just choose B equal to minus X, V equal to 1. You do this integration, that's equal to, that's the density. So this way, the corresponding Y, the unique state distribution for this diffusion process is a standard normal random variable, okay? Normal random variable, and it's a equation characterizes standard normal normal random variable is guided by this. This is often called the Stein equation, right? People first read Stein's paper, mystify. Why the normal random variable characterized by this equation? Oh, that's just a basic algebra relationship. BAR for this process, BU process, this particular BU process with a drift of negative X, variance parameter equal to 1. That's called OU process. So standard normal is nothing but state distribution for the OU process. All right. So this is right. Our generalization, what's going to talk is all related to this. So we are not going to use standard normal. We're using some other density functions, but still it's related to very similar to this equation here, right? This equation here. So this is the base algebra relationship. So I think before I move on, carry out the program, okay? Now introduce Markov chain again, connect which diffusion process to be identified. Are there any questions so far? So particularly on this informal summary, this one here.
I have a question.
Yes.
So you said for all functions f, what if we consider a smaller class of functions, say polynomials? Would the equation still work?
Yes, polynomial with some kind of maybe truncation. But the problem with a polynomial is that this expected value may not exist, right? So if y is something like the normal, has a right tail goes down to 0 rapidly, then polynomial no problem. But for other y distribution, I think generally, if you see the form here, right, I expect the normal should be fine. Yes, that yes, it's related to density y. Do the y have enough decay? Yes, the density.
Okay, thank you.
Mm-hmm.
I have another question, Professor.
Yeah, sure.
So does it hold when this function f is a complex function? For example, it's a characteristic function of y.
Yes, it holds. Yes, yes.
Okay, thank you.
Mm-hmm. I mean, to me, is if you use right. So the question is it better to use Laplace transform or the characteristic function? It depends, right? Yeah, even if y is a completely non-negative random variable, sometimes for example, in my work with Professor Miyazawa, we actually did occasionally use complex test functions. So that's at this point, I think it's yeah. Okay, any other questions? All right, if not, then I'm going to get to the connection Markov chain and this diffusion. Okay, so this is a let's see. So this is a I need to keep track time. Okay, so something that I think I'm going too slow. It sounds like that. Maybe the banker, you should alert me. Okay, whenever you think it's appropriate. So let's consider a Markov chain, discrete Markov chain. And so this has a distribution, and this is Markov chain. let's x0 initially start is having the station distribution, okay? Then this is a stationary process. In particular, distribution at 1 and 0 are the same. Therefore, you take its value at 1 or times 0, they are same thing, right? Because stationary. So this is for NAF, okay? Whenever this expectation exists, okay? So let's since we use W notation a lot, let's call W equal to x0, and whose station distribution may be difficult. The W distribution of W may be difficult or impossible to calculate W, okay? And x1, that's the state for next time at the next time. So look at difference, the change is called delta. And so this equation here is the same thing as I'm copying down this first equation. First equality, I'm copying down previous one, I'll copy it down. The second thing, I'm going to conditioning on W, okay? Conditioning on W. So, and this is, so what's inside this one, I'm going to denote this by G, okay, G. And if I do the Taylor expansion on G, that you see here, then this is the equal to space value GW. And if I ignore the other term, just Taylor expansion, just keep two terms, I got this one here. All right, so let's just pause for a moment. So I started with this, from stationarity of the Markov chain, okay? And I got for any functions, this is almost true, right? Almost true. This is for prelimit. And you expect in the limit case, this would be true, equal to equality. And what you see here is this one here is nothing but related to diffusion process, right? So, or the BAR you saw earlier. So in this case, if I ask you to have to pick a V for me, right? Pick a V form, which V do you pick, okay? Which diffusion coefficient you pick? And I think certainly, since this is almost equal to 0 here, almost equal to Taylor expansion for the prelimit, and I know I pick a V and the random variable I want Y is characterized by this equation, so I probably should pick V equal to half A, okay? Half of this function X. And that is equal to this change here, delta squared is the value. And so indeed, that's my first choice V. My first choice V equal to V1, okay? Function V1. And I put index here, sub-index, okay? Index here, V1, because I do want to consider other possibilities, okay? This time I don't want, this is natural choice, okay? V equal to V1 is natural choice. And I would say most people, if you do, you know, if you're familiar, if you spend a few minutes, maybe just a few seconds on the previous slides, it will not be too long for you to figure out, to choose this V1 as your choice. And therefore, you have once you pick, you already know V, B is a drift. V is related to the second order of variance parameter of this Markov chain. And then corresponding to the solution to this Y, this is the one random variable you probably will propose to approximate this W, okay? All right, so that's this first one here, slides. The next one here, I'm going to now illustrate this idea through three models, okay? One is discrete time model, hospital models. This is actually extensively discussed. This paper is exclusively discussed in this paper, okay, introduced in this paper, okay? The second one is discrete time AR model, and that was in Blanchard and Green paper. The third one is in the continuous time Erlang-C model. This is continuous time model, Erlang-C model, and many of in the audience are expert on this subject. Okay, so I'm going to use this third model, discuss third model as well. I should mention that all details are in this paper. So today's talk is really talking about this paper, Braverman, and jointly work with Braverman and Xiao Fang. Okay, so this paper is currently under review. Okay. It's certainly available on archive. All right. So the hospital model is this one here. So imagine you have a daily arrival, 8K. So how many people want to be admitted into hospital, but maybe you cannot be admitted, okay? DK is a daily discharge. How many people will be discharged from hospital? And XK is a count, the count. So customer count. Customer count, to be concrete, say midnight, we call it midnight customer count. Around midnight, how many people are waiting for beds, and plus those people already in hospital that's already occupying a bed. Okay, so that's XK. So the next day, the customer count equal to today's customer count plus the arrival for the day and departure for the day. So that's clear. So we assume that AK is the IRD from day to day, the IRD integer valued. For example, Poisson random variable with the parameter lambda. All right. And we DK discharge is a particular model, is a binomial random variable. How many people currently occupy beds? This many. XK is the number of patients you have, and minimum N is the number of beds in the hospital, and that's how many patients are occupying beds now. And each of them have probability of mu going home today. So so this is the number of discharge for day K. And you may not like this model, maybe that's too simplistic, agreed, but that's a starting point when we started this hospital model. So SK in this setting, SK is a discrete time Markov chain, all right? So the setting we're going to look at is N is large, number of beds is large, lambda is also large, okay? The daily number of patients to be admitted, that's also large, okay? So that's a setting. And so if familiar condition, if lambda familiar condition, if a daily number arrival less than n mu, n is the number of beds, each one is getting out at the rate mu. So if this is less than 1, the system is stable. So the Markov chain has station diffusion, okay? Now, actually, I was actually first opinion, I actually was annoyed that this pi is difficult to compute when n is large, and the rho is close to 1. Okay, it's difficult to find a stable numerical algorithm to compute the station diffusion pi. Okay, so so we're going to resort to approximation, and has this scaling parameter n delta. And delta, think of this equal to 1 over square root of n, okay, delta. And we have scaled centered around n because it's a natural setting centered around this n or a number close to that because it's a large system and then you want number of patients in the hospital should be close to n, either, right? You don't want too many people waiting. On the other hand, you perhaps don't want too many beds empty there, okay? So that's, that seems natural scaling or centering. So we're going to look at this parameter regime, and it is called, it's very similar, or you can call it half-and-width regime. Lambda is arrival rate, is large, and a mu service time is a small. Now this actually is a bit surprising to us. This is different from half-and-width regime traditional one. Oh, my slides is not synchronized. Okay, I don't know what happened. Let's see.
Jim, we can see your slide 17. We could see now it's 16. Yeah, this is.
Are you right? You can see 6. Okay, which slides now? 17. Okay, so it's just, I have 2 monitors. My monitor is, the other monitor is not responding, so I ignore that, right? So you are on the right one, okay?
Yeah,
so for some reason, that okay, good. I'm worried, something. So now, good. It's all good. So you see that I'm using the pointer here. So I'm looking at this half-and-width regime, right? The equation 3 you saw, right?
Yes.
Equation 3.
Yeah.
Perfect. Okay. All right. So now let's look at so in this case you have BW. So what's going on here? Now I lost, I think.
Now it's a bit zoomed in, I think. Yeah, this is
okay?
Yeah.
Okay. Yeah. Okay. So remember earlier that we have formula for B for Markov chain, so because this model is a Markov chain model. So BW can be computed explicitly, A drifted computed explicitly, A can be computed, and these things that so that it's just show you that it can be computed explicitly. So now I'm going to show you some. So this is the first choice, the V1 choice. Okay. V1 approximation. So since B and A is computed, so V1 approximation here, that as we said, we just choose V equal to V1. Okay. So again, so in this case, we're going to approximate W. W is remember what's a W? W is W is equal to delta X minus N. Okay, so X is the Markov chain, represents the total number of patients in the system. Okay, those occupying beds and those waiting. Minus N is the number of beds, and delta is scaling parameter. All right, so we're going to approximate this W by a random variable Y1, and a Y1 is characterized by this equation here, because we choose V1 is equal here, right? So okay, here's Y1, but in the equation here, the typo Z1 should be Y1. Okay, Z1, Y1, same thing. All right, that's certainly one possibility. So let me move on to the next slide. Another possibility is, if you look at this A here, B is in the order lambda delta. Okay, A is in the order, here the term delta term, but everything here is like this term part is delta square, and this term is delta cubed. So if I drop this delta square term, delta cube term, and I got something V0. V0 is just keep this term here. So V0 is a half. 2 delta is a delta. So this V0 is constant. Okay. So which means if I choose V0, meaning that the diffusion coefficient is constant. Okay, diffusion constant. And I should say that in the diffusion approximation for QE networks in the last 30 years, most approximations, almost all approximations using this form, that the diffusion coefficients are constant. Okay, so this one here. And I listed just a few exceptions here. Okay, one of the papers that Glenn and Ward with Glenn and Amy Ward, and they actually discussed this possibility using the non-constant diffusion coefficient to approximate a queuing system. All right. So now you have two here. We have V1 approximation and a V0 approximation. Now we want to see the next few slides. We're going to see some plots. Okay, numerical example. All right. So this is the first one here. So this is the numerical example. You see that it's okay. 500 bits. Okay, 500 bits. Okay. So this is the 500 bits. And V1, V0 appear to be similar quality. So V0 is not constant diffusion coefficient, not too bad. So it's this. Okay, they are off a bit here, off here. All right, but other areas seems to fit quite well. Okay, this is for smaller system, 18 bits. Okay, smaller system, 18 bits. And again, looks like similar quality. But in our paper, in the paper that I did with Panyi, we found that when you try to get next level performance, time of day performance, not just midnight performance. Okay, midnight performance. then V0, V1, quality of V1, V0 actually come up sharply. Okay, the difference come up sharply, and then with V0 approximation cannot get meaningful good approximation for time of day performance. All right, but still qualitatively, if you look at this picture, V0, V1, not too much different. Okay, can we do better? All right, indeed we can do the third moment. If we continue on to the third moment, got a third moment C, and a fourth moment D, right, E, etc. All right, I do the something to do the further computer higher moments, you get these. And the point is that a third moment here, there's maybe delta square. I can ignore the cube delta cube term. Ignore delta cube term, and this term from the fifth moment is completely delta to the cube term. Maybe I should ignore that. So let's see if we can do better. So indeed, we're going to use V2 approximation and V3 approximation. So let me just introduce this maybe slowly. First of all, V2 approximation, I'm going to not just using first two moments, okay? First, drift, diffusion coefficient. I want more. I want third moment. This is the first moment, second moment of the, remember, delta, the changes between the two time point of Markov chain, okay? So I wanted the third moment introduced, and that's V2. You see V2 is exactly use first, second, third moment also use that. And V3 is using first four moments, okay? First four moments, and then they all use. And eventually, I just V3, if I ignore delta cube term, it's actually got simpler expression here. It's this one here. So now let me, is that expression not easy? I'm going to motivate, or let's say prove, give you some idea how how did we get this 12, okay? I do want to get to that. But I'm not going to get into V3, etc. Okay, but it's also in the paper. So, but let me go to the numerics. Okay, so same model on the hospital model, same 500, same parameters. Now you can see. Okay, this is a V2 approximation, right? This is the green line here, but V3, the red one is right on, okay, right on. So you can see even this visually, you can see V3 is a improvement, clear. It's a significant improvement. So it's not accidental. Not right. We first did this, then later we did this analysis here. You see this here, right? V3 is using the fourth moment all the way to the fourth, also use a D, right? So if we just use V3, V2, just using the third moment, then you see it's not justified, because in the fourth moment, you also have delta square term. If you ignore D, delta square term ignored, and whereas C and A, or you have delta square term there. So if you ignore D, why not ignore C as well, right? So it's not surprising why the V2 this is not performed as well as V3. All right, so that's the first picture here. Let's see what's the, okay, let's do some numerics here. So further numerics, this just to show you that the difference is significant between V1, okay, V1 just using the, okay, I cannot, shouldn't touch on, okay. I'm not used to this one to for presentation yet. Okay, so you see here, V3 here has qualitatively here has much higher accuracy, okay, than V1, okay. So that's this one here in terms of first moment, in terms of second moment, Okay, compress them. There's also, we look at the tail probability, okay. Tail probability, this tail probability itself is quite far. By the way, this is after do the long simulation because numerically we cannot compute. Numerical computer, you have to do very long simulation to get this kind of confidence interval, okay. So you see that the accuracy of V3 is better than V1, okay, significantly. So let me just point out here, the first bullet point, it says that we did not reported here, V1, V2, they are qualitatively similar quality, and they are not slightly better than V0, but not in the order of magnitude, okay? But they all worse than V3, okay? All right, and it numerically also appears to be, it's the decay rate for the like rate convergence for V0, V1, and V2, they all appear to be go over 1 over square root n or delta at rate delta. Okay, that's the rate. Okay, apparently. So now let me spend a few minutes deriving this V2. Maybe I think I don't have time to do this. 17 now. No, I think I skipped this. Okay, so basically, okay. So at this point, V2 approximation is a how do you get V2 approximation is a mystery, right? It's a bit of mystery to you, and that's maybe unfortunately that's the central part of this talk. But I don't have time to get into that, and this slide try to explain that. Okay, so let me just move on. Okay. So now the question is, can we do some mathematics with that? Unfortunately, for V2 approximation, we can't. Okay, we have not able to. So this is the one with the open problem. We believe that this V3 approximation, so W is related to scaled patient count in the hospital, minus that Y3. We believe this is a converge at this rate delta square. Okay, delta square. And this distance is the fastest Stein distance, okay? Fastest distance between two random variables. Now, what is known for Y0, you know, in this paper, we prove this delta to the half, okay, convergence. And later on, there's a paper by Fang and a former student at Cornell with Peng Yishi, and they wrote a paper, and they proved for Y1 of V1 approximation, V1 approximation, also have this rate. Now, you know, based on numerics, just saw earlier, we believe these rates are suboptimal. This should be converged at rate delta, okay? But likely this is just a proof technique, okay? It's a limitation of the proof technique. So this result is not optimal. Anyway, this is open, okay? It's completely open, and everybody is welcome to work on this problem if somebody, you know, you want willing to prove this, okay? All right, so let me quickly flash out the second one here is a model, is the AR model. And again, I need to be quick here. AR model, it's this one started by Glenn and Blanchett, and they want to demonstrate the H-worth method, expansion method, can really get a high order approximation, get correction terms is normal approximation. Okay, so we can develop the V approximations using particular V2, V3. Let's look at V3. V2, V3 approximation, that's from our approximation. The H-worth is from Glenn and Blanchett, okay? And H-worth is known to be of problem from tail, right? The tail, it's known that sometimes cannot make the approximation to be accurate everywhere. So that's actually a known problem, and it's very prominently here. Now remember, this alpha is equal to 0.5. It's not close to 0. So if alpha goes to 0, you have central limit theorem. Okay, central limit theorem is normal limit. This one clearly the shape doesn't look a normal distribution. So that's right. This when the parameter is not really in the limit. What you do there, that's really this, I think, Stein method, or this the method that I'm advocating today is really shine, that you are not in the actual limit regime, okay? So here you see that these approximations are better than the Edgeworth expansion. And of course, when alpha is very small to the limit, any approximation will work. So basically, that's the point, okay? All right, so let's quickly go to the third part, the last part of this model, okay? So the Erlang-C model, and many of you are familiar with, so it's the MMN model here, okay? So I'm not going to get into generator, except this R is the so-called overload, lambda is arrival rate, is large, mu is the service rate, N is the number of servers. So the overload less than N, okay? And we centered around the overload. And it's a scale parameter here, delta is 1 over square root R, overload, okay? So that's that. So this time you can compute A, B, right? B the drift parameter. A is this the one here, C equal to delta square times that. So if we use V1 approximation, then it's half A that we did earlier. If we use V0 is equal to mu. I ignore some high order term, that's got V0, which is equivalent to say set X in AX, set X equal to 0. And that's in general, it's true. That's this 0 is representing the equilibrium of the fluid model, okay? So in the, but this is a scaled parameter, okay, scaled. So it's scaled, the equilibrium becomes 0, but the fluid model. So generally, this is diffusion coefficient. So if you set X to be the equilibrium of the fluid model, that gets you constant coefficient, okay? That's traditional diffusion approximation has been done in literature, okay? So that's that. Okay, so let's see a few plot. So we have a constant one, that's V01 approximation. This is V0, this is the green one. The red one is the V1 approximation. You see that V1 is almost indistinguishable with the exact one, okay? So that's for N equal to 25, okay, 25 servers. If we even get to smaller N, okay, not quite in the limit, okay, smaller N equal to 5, you can see now the difference between the constant one, V1, and V0, and V1, so this is V0, this is V1, and the difference is much more prominent when system is a smaller here size, away from the limit regime, okay? So the difference is much more that. So now I've got get you all this, the plots. So here are a few mathematical results, and then I should, because I'm near the end of my talk, so let me say. So the first one says that in the Erlang-C model, the W scaled the Q size, okay, scaled Q size, or system size, scaled Q size. Compare with this V1, this normal random variable, I didn't give you, so V1 random variable, okay? The V1 approximation is under this metric, okay? Under this metric. This metric is a slightly different fastest Stein distance, okay? Fastest Stein distance require H to be Lipschitz 1. And this one require H prime also Lipschitz 1, okay? So this W2. So this distance is over some absolute constant, C over R, okay? Now, if you compare this result with the next one here, Y0 approximation, and this one, Y0 approximation is the one that used in the half and weight, used in the Manabang, Ita Gervich, and one paper, right? Pretty much all the paper. you this is the result that that's approximation being used in literature, right? So this one is a 1 over, this should be y0, okay, y0 here, it's a typo here, y0. So it's 1 over this. And I don't have time to get into this. First of all, it's Ivy Mandelbaum, Ita Gervich, and Junfei Wang. They are the first paper point out is the universal approximation. By universal, meaning that this constant C clearly does not depend on the load, does not depend on lambda, does not depend on mu, etc. Right? So it's one approximation is applicable to all kind of parameter regime. So basically, it's universal, right? So we see this Y1 also enjoy universal approximation here, right? This is also absolute constant, although we didn't get into the absolute number there, okay? So that's that. You see that there's a order of improvement in terms of rate convergence, okay? That's that. In addition, we can also look at the tail, okay? Why do I care about tail? Because some performance measures like 1% customer abandonment or 5% customer waiting there 10 hours, etc. Right? These are the tail probability, and we often want to care about these performance measures. So co-Markov distance or a faster distance doesn't give you that because it's not guarantee. So look at tail directly, comparison. And if you use a high order one, that Y1 is a high order one, is this tail, okay? This kind of error. And if you use the Y0, okay, the classical one, the Y0, classical one, that's in the half and width, then this tail approximation only good when Z is not too small or too big. It's not far into the outside. So basically that if you use a half and width, traditional half and width paper, Z0 approximation, there's no guarantee large deviation approximation will be good, okay? Whereas in 15, if you're using our high order one, that's even good in large deviation. And we actually proved this and also numerically verify this perhaps is the optimal one. So we verify that this is the actual computation of the tail, okay? So one is the high order one, basically tail is continually good. Doesn't matter how far outside in the region to the right. So this is in a high dimensional case, the high order one also, this is 2-dimensional, okay? High order one also is good, is better, okay? So this is for 20 servers, and the service time is distribution is the Coxian phase 2, it's a phase type, two phases. So in the limit, this one, in terms of diffusion limit, it's a 2-dimensional diffusion, okay, 2-dimensional diffusion. This time, this curve here, the burst curve, the station diffusion for V1 is a traditional, V0 is a traditional, V1 is a high order. Bursts need to be computed numerically, okay? So you see that the high order one, it does perform much better. Again, that for the system very large, there's no difference. Really doesn't matter what you system very large, which applies using constant diffusion coefficient, it's perfectly okay in the limit case, okay? So this is the case actually you see that begin to see the limit of the computing the exact one. The Markov chain is a very large Markov chain. You do a lot of truncation, then you need a big machine. And this is something that time that that was the exhaust limit of our computational capacity. So the diffusion approximation was provided scalable in this kind of model here, scalable in terms of number server, okay, way to compute performance. So let me end here that I don't have time to get to that and conclude this talk. So I was, okay, so Taylor expansion can generate V0, V1 approximation in both one-dimensional and multi-dimensional case. So that's quite standard, okay? That's standard, you can do that. At this point, for high order, V2, V3, we did this talk, we did this paper, our paper did one-dimensional. We don't know how to do this multi-dimensional case, okay, at this point, okay? Also, we didn't prove, okay? We didn't prove for the AR model, Husky model, we didn't prove high order convergence, okay? In the Erlang-C model, we did prove, right? I present the two theorems. We did prove that it indeed achieve high order, the V1 approximation, okay? And in the last two slides, multi-dimensional case, that's V1 approximation. It's an open problem to prove this one indeed achieve high order performance convergence. So in the two-dimensional case or multi-dimensional case, we don't have that, okay? And I didn't have chance to get into detail on the proof, right? So just point out that in using Stein's method to attack this open problem, the likely bottleneck are gradient estimate Poisson equation solution. So as I mentioned at the beginning, I said that in the most approximations using standard normal as target random variable. Standard normal is a state distribution for the OU process. For that, Poisson equation well studied. It's a textbook, this kind of gradient estimate for normal random variable, it's textbook results. But for us, each time you use this method, I call it engineering method. You need to engineer your new solution, new Y, new Z. Each time engineer that, you have a new Poisson equation you need to resolve. Therefore, for that Poisson equation, you need to estimate gradient, and that you need a new work, right? So I think I should stop here.
Let's all thank Jim for the excellent talk.
Thank you.
So if there are any questions, please feel free to unmute yourself and ask.
Can I?
Sure, please go ahead.
Yeah. Hi, Jim.
Oh, David. Yeah.
Question about one of the last slides. When you improved C over root R to C over R approximation in the Erlang, I think it was for the Erlang model. I assume that this is tight, right? In the regime where Q size of the order root R. That's probably not improvable any further, right?
You mean this result?
Yes. Yes.
I think it's not. Yeah, we believe it's not improvable. Yeah.
You believe, but it doesn't follow from something like Barry Essen type kind of consideration. It doesn't follow that you can't. Barry Essen tells you can't do better than 1 over root n for the CLT. You don't have.
Okay. Yeah, I think this today I didn't get into this different matrix. Okay, David. I mean, here is the Wasserstein distance, right? This W2 is very similar to Wasserstein. And Barry Essen is in terms of Markov, okay? Markov is really, you need to have a worst case scenario, right? That's something. So I think in this case for Y1, even in the, I didn't display for Y0 here, the classical one for Markov distance is this rate, okay? The Markov distance is this rate. And I believe for Y1, we believe that it's also this rate. You cannot improve.
Okay.
So does this answer your question?
Yeah, and it's a belief. You don't know that.
For Y1, Anton, do you have anything to share?
Yes. Sorry about the background. So numerically, I've confirmed that the results in these two theorems are tight. In other words, the numerical errors converge at the rates that they're shown. If you talk about the Kolmogorov distance, it's all 1 over square root of R, even for the Y1 model.
Okay.
And if one more point, you can do lower bounds. So just like Barry Essen said, well, Barry Essen said you cannot do any better. In this case, how we prove these is we have the explicit error. We have equality, in fact, and just it's up to us to work on, to think about how hard we want to squeeze all the bounds or how sharp we want them. But my personal belief is that all these results are tight.
Thanks. That's very clear.
Z, you had a question?
Yeah. Hi. Thanks for a great talk. So I have two questions, one high level and then one low level. So I guess the high level question first. So basically, you gave a good overview. You gave an overview about using Stein's method to basically approximate dynamics. I was wondering, has anyone used this type of method to approximate control problems? Maybe like looking at the generator of each action of a control problem or something like that.
Your voice not very smooth. I missed something. You said, have anybody?
Sure.
If I interpret your question, have anybody used Stein's method to look at true problem, real problem, or what?
To look at control problems rather than just instead of just modeling a Markov chain, modeling a Markov decision process.
Yeah, I think yes. The answer is I think Ita Gervich and Anton Braverman, and I'm not sure who's third person. Maybe Junfei Wang. They had a paper on this subject. So it's published in Operation Research, I believe. Published maybe a couple of years ago. Yes.
Okay, great. Thanks. I will note that. Okay, and then the second question is low level, which is about the hospital model. So you mentioned that V2 was worse than V3 because it used some but not all of the delta squared terms.
Right.
So V1 also, if I remember correctly, used some but not all of the delta squared terms.
Right.
But it ended up being way better than V0. So is there a rule? Is there a specific reason why V1 was still a good idea, or was V1 really just as bad as V2? Or
so let me correct you first of all. I think my message was that V1 was not significantly better than V0. Indeed, they are V0, V1, V2. At least V1, V2 is right. V1, V2 they are numerically comparable, and actually it's justified because they do contain delta square term, and you cannot just ignore everything. So I think the improving over V0 is also questionable. I think there are some improvement. I mean, in the I mentioned time of day performance. Actually, next level that seems to improve, but it's not. I think they converge at the same order. That's numerically at least. So numerically V0, V1, V2 they offer the same order of convergence.
Okay, great, thanks.
Are there any other questions?
I have a question.
Sure.
So in this example, Y0 is a Gaussian distribution, right? So what is Y1? What's the stationary distribution?
I think in the hospital model, Y1, I think we got something called a peer. I mean, we try to find a name. It's something very similar to what a Poisson distribution. Something that really doesn't make much sense, right? If it happen to be there's a name to it, just accidental, right? So because it's we are engineering so many random variables, and the only thing why cannot move quickly? Which one I want to go? Come on. Okay, here. Not even this one here. So that's the distribution. Yeah.
I see. It's some kind of Gibbs distribution.
I don't know. I mean, because there's something here, right?
Okay, so
there's something here. That's something. So it's I think in the hospital model in the paper that that's V1 approximation in my paper with Pang, I think the name Poisson showed up somewhere.
I see. So does this mean that, I mean, thinking about the Erlang-C model, does this mean that the Y1 distribution as R goes to infinity approaches a normal? Because Y0 is a normal, right? And then the W sequence.
So the Erlang-C is easy, not easy. Let's see. Erlang-C Y1 model. Let's look at the B.
I guess actually what I'm trying to understand is how you're able to improve the 1 over square root of R to 1 over R. Intuitively speaking, the distance to Gaussian is somehow 1 over square root of R, but then by refining that distribution, by looking at a more intricately defined distribution, you're able to get 1 over R, but in the limit, both the new distribution also converges to Gaussian. Is that correct?
Right, but the thing is, right, the Gaussian is, right, in the target, the limit case, they are same, right?
Mm-hmm, mm-hmm.
So, yes. But okay, so it's misleading here. I think I'm using, right, this depending on, so this is a very, right, what's going on here? Okay, so I think I cannot write something, but you see my first display. This so this what this W depending parameters, right? Okay, let me see if I can write. Why cannot write? This is something that let me use different way to share. Okay, so this is annoying here. I think after all, it's a not good way to use a different way that I can share that I can write. Today's talk, I think taught me something. I should use stick with the familiar technology, right? So that's a big lesson. Okay. All right. Yes. So so this depending on delta n, right?
I see.
Is that clear?
Okay. Yeah. Yeah.
That's a pre-limit.
Right.
That's not surprising.
Correct.
This also depending on delta. That's limit. But it's not limit. This also depending on limit. I'm compare right. This is from diffusion process here. Y.
Okay.
Okay. But it's a function of delta, function of parameter.
Okay.
Is that clear?
Yes.
So,
yes.
So I'm comparing two models now. This is a diffusion model. Okay. I compare two models.
Okay.
Right. They both converge to some limit. Let's say Z star.
I see.
Okay. Something.
Right. Got it. Okay.
Mm-hmm.
Okay, then a related question is the following. So we know that in for central limit theorem, in Berry-Essen theorem, the 1 over square root of n is tight, as you just mentioned in Kolmogorov distance. But in similar to how you were able to improve it to 1 over R in Erlang-C by going to a new distance, the W2 distance, do you think we can do the same higher order approximation for central limit theorem and then get a 1 over n rate of convergence?
Okay, so for that matter, it's interesting that I think today I didn't have chance, or I don't know enough, didn't age-worth expansion, right? First of all, age-worth expansion is really try to next order, right? To the higher order. So that's the first thing. Now your question is it possible by changing matrix can improve Berry-Essen bond to get the next level high order, right? Prove high order convergence. I don't know, right? I don't know. I mean, that's a speculation, certainly. Yeah, I don't know. I think it's interesting speculation.
Okay, thanks.
Mm-hmm.
Varun, you had a question?
Yes, Jim, like I was wondering if you could, so I think I know what happens in going from V0 to V1, you just keep more terms of E of delta square. I don't know what happens in going from V1 to V2, because somehow you're borrowing the terms which go with third derivative of F and put them next to the second derivative of F. And I was wondering if you could sort of give like what's happening there, like what process is the model Z, and like why could it be a better approximation than V1?
Yes, this is something that I write in the interest. I mean, very unfortunate. My poor management, apologize, poor management timing, and this is the most important technical slide, right? So something, because I don't expect, right? I didn't know this right methodology could be possible, right? But this is something that this is truly something new, right? So this, so you basically want to ask me, how do I get a V2 approximation, right? So that's really the question here. And I think here the audience are free to go, right? So we are not, the audience not in hostage, right? So I spend maybe 2 or 3 minutes on this. Is that okay? Let's see something. So let's see. So we want to get this, right? Identify V2. Is that clear? That's the objective.
That's right. Yeah.
So that should be W, big W, right? So that's something. So we do Taylor expansion to the third order, Taylor expansion third order. That's this, right? The Taylor order. Okay. Now we have a first order, second order, third order. Now you don't have diffusion process defined by F triple prime, right? Here, something we don't have, never seen like that, right? Such process doesn't exist, something, okay? So this is the, right, this is a term that's difficult. So you can expand to the third order, but you cannot deal with that, right? What to do with that, okay? So let's remind that the previous expansion for Taylor expansion is the second order one, that's got this, right? Okay, this is for all H is true. This is where the thing, like this method that I want to clearly label this Stein's method to do engineering solution, to generate engineering solution. And this is the, because this is the Stein equation, okay? Or basic algebra relationship, Stein equation. So this is Stein equation required for all H to be true. All H to be true. It's not just one H, right? Here it's for all F is true, okay? So now fix F. I look at this equation 13. I'm going to take spatial form H. H equal to the previous F, this F used in the next line here, and this one here, the coefficient. Okay, so that's the H. Okay, so you choose this H, satisfies this, the first derivative equal to that, and then you do the second order derivative, and then you plug this H double prime here, and H prime over here to this equation. So I'm just plugging, copied on 13. 13 becomes this one, the last display. Varun, do you see?
Yes, so, but it's missing the first term on F prime, right? So to...
Okay, hold on, just that. So I just want you to look at the last equation here. So this is derived from 13, pick spatial H. This one, okay? So what's the point to have this one, last display? Last display giving me something about this term. The red one, the term, in terms of the F triple prime, in terms of F prime, double prime, F double prime. Okay, now I'm going to this feedback to here. Now I convert this equation here, this third prime, F triple prime, F third derivative is gone. No more F triple derivative. Everything in terms of first order derivative, second order derivative, and a bunch of second order derivative are moved over here. And I collect the coefficients in from second order derivative, that's my V2. I know this is real time, maybe not easy to something, but I think at least rough direction that's going.
do you think like it might be possible to prove V2 is somehow better than V1? I mean, I kind of see, I mean, all of these are approximately equal to 0, so it's unclear. Like, I mean, what's the order of improvement, but do you think it might be possible to prove?
I think my guess is that within next 12 months, the proof will happen.
Okay, thanks.
Yes, it's not just I believe in this. I think a proof is within strike distance.
So Jim, you can keep doing this and then get like a sequence of V's, like V0, V1, V2, and so on, or is there anything stopping you at some point?
Yeah, you can keep doing this.
I see.
Yes, that's true. That's so in our in our model, the hospital model, it's clearly right. V2 is not enough. We need a V3, and it's the key that I didn't put on the AR model one. The key is to get with yes. I mean, you just look at this where the. By the way, in terms of if you just care about do the engineering solutions, you don't need any scaling. Okay, you don't need to do any scaling anything. Okay, you don't need eccentric, don't need any scaling. You just do the Taylor expansion. You can do that. Okay, so something without any scaling, you can do something. But scaling does help us to identify which term, okay, should be kept, which term should maybe can be ignored. Okay, so right, so this scaling tool tells me that maybe this term that I can start to ignore. Delta cube term can be ignored. Yeah, but you shouldn't ignore D2, D. For D, we need to use a V3 approximation. Yeah.
So Jim, I have a quick last question. Like all your results are non-asymptotic, right? As you said, like scaling is not important, but somehow in this approximation, the Huffington scaling is playing some role, possibly, as you said, to ignore certain terms and in error terms. So is it possible to use a different scaling and maybe to look at a different diffusion? Because if you use different scaling, maybe it will converge to a different diffusion. Now, from that diffusion, comparing its generator with the generator of that diffusion, is it possible to get an improved bound for different scaling of delta here?
Okay. Right. This is coming back to it's an excellent question. Okay, coming back to the why I cannot go easily to the. There should be something that can go easily. Okay. Yeah. Right. So first of all, okay, so these results here, right, it's universal constant, right? Second of all, this y0, this y1, they all depending on lambda, mu, and n, okay? So this all depending parameter lambda, mu, and n. And so again, this related to Siva's question here. So whether yeah, it's right. So here my only requirement is this y1 is easy computation, right? Easy computation. So it's given, the density is given by this format, Vxx e to something, right? So this one here. So that is in this format. And but these parameters here, everything here is involving lambda, involving n, mu, involving n. So it's not limit per se. So I don't know how to answer your question here. Something that is there any different scaling, different something here, right? That's why I said this here, nothing to do with scaling here.
Yeah,
and
like if we are beyond Huffington, which we often call super Huffington regime, then we see a different diffusion coming up as the limiting object. Now that is also, of course, asymptotic. Now we can just start from that generator of that diffusion and compare it with the preliminary.
It's a completely. I think now I see your point. So this same object y1, same object is. So if you narrow down, adding relationship between n, lambda, and mu, it's possible you have a different, this would be 1 over r squared, have a different c depending on the parameter, particular relationship. It's possible. I think potentially. Yeah, but I'm not sure now. I think that question, I don't know whether I believe that. I mean, something can improve 1 over r. I'm not sure, but because the question is the 1 over r is the fundamental, right? Why you even care about system in that region r go to large, right? So something that's not clear.
Great. So
Amber, thank you.
Is there any other question? Otherwise, let's thank Jim once again.
Thank you.
Let me stop the record.
Thank you. I mean, the banker, I don't want to impose too much on you. I'll be willing to spend a few minutes here. So anybody want to chat just casually or anything, I'll be very happy. I can stay for a bit longer, but yeah, I'm not sure what's your protocol. Yeah.
Oh, okay. So Jim, I have a few more questions, so I can stick around. So others
okay. Yeah, sure. I'll be just chat for some time. That's fine. Will be fine. Yeah.
I'm still struggling to understand the big picture. So as you said, there is V0, V1, V2, the whole sequence of approximations. And then what the slide is saying is that if you go from V0 to V1, you go from this 1 over square root of r to 1 over r. Then the question is—
No, that's model to model. That's really the big picture is that which one is the high order depends on model.
I see.
Depends order. For Erlang-C model, is from V0 to V1 to go to high order. And for hospital model, clearly it's not from 0 to V1, not even from V1 to V2.
I see.
It's V3 is the high order. The numerically.
Okay.
So that's the open question is to open problem. Can you prove that? Right? Can you prove that? Right? Can you prove that it's a V1, for example, it's delta order convergence rate? It's that's optimal one, and a V2 indeed you can reach. V3 you can reach delta square. That's a big picture.
I see. So then, is there an intuitive reason why for like this model V1 is higher order, whereas for the other one it's
I think it's depending on the parameterization, right? I mean, if you think about what's alpha square, delta square, something, it's related to parameterization of the model. So I think that's maybe not surprising, right?
I see.
Right.
Got it. And so it looks like the belief is that as you keep increasing this order, at some point you'll go from 1